Let's say what are the other considerations. Let's look at IP storage briefly. So first let's look at iSCSI. iSCSI is also very interesting because really what happens is you have the I'm going to assume the iSCSI software driver. We don't tend to see too many iSCSI hardware drivers nowadays, especially because CPUs have become so fast that the extra overhead of running the software driver is negligible. Okay, so you have your iSCSI software driver, right? And the way it, as we've seen before, that we actually make this work is by we create a port group. Okay, we assign basically iSCSI traffic to it. Here's your VM kernel. Let's say it's VM kernel. Let's use 4. I could actually, just to keep things nice and clean, and it's always good to have a nice clean design here. It's just easier to operate. I can say my VM kernel 5. It has an IP address. Is also only going to be used for iSCSI traffic, and you can do this in your distributed virtual switch, as we have seen before, or as you already know. And the nice thing about this is that you would then assign this over to a NIC team. You could say, for example, let's try a different color here, VM NIC 0, and say VM NIC 2, and I'm deliberately not putting 1 in here because I'm making an assumption here that this is VM NIC is defined on the 10 gig converged network adapter that's on the A side in a UCS, and 2 is being defined on the B side. So I'm actually physically using two different converged network adapters. Okay, it's just a fine point on something. So I can basically say this is using VNIC 2 and VM NIC say 0. Now for iSCSI, there's a special thing that one has to do, because the way I've defined it, it won't actually work. What you have to do is only one of those NICs, okay, is active. Now while I've defined it like this, the other one has to be defined as unused. Okay, so if you happen to design it like this, there really is no need to define it like this. And I guess I came to this point from the opposite direction. Okay, so you can only have, and that's the thing, only one active physical NIC, okay, for iSCSI kernel, iSCSI VM kernel port. Okay, that's the reason why. So in this case, obviously, what I would do is I would use VMNIC 2, and I would not even worry about VMNIC 0, or I would worry about it because I would have to configure it as unused, because it is available and it is being seen by the virtual switch. So you are now able to route your traffic through VMNIC 0 and VMNIC 2, two separate. And the reason you can do it because iSCSI and iSCSI uses multi-pathing. It does multi-pathing I/O, so your traffic is multi-pathed. And if you had a chance to review my earlier course on vSphere virtual networking, I showed you a similar configuration, and we talked about multipathing I/O, and I showed you the the multiple active paths that were there to my iSCSI array. So it does. So iSCSI has multipathing I/O. Okay. Now in the past, and next we are going to talk about NFS. NFS3. No multipathing I/O, but NFS4 has. So NFS4 has multipathing I/O. Okay, you can have multiple TCP sessions. So when you use NFS in the new release of vSphere 6, you have NFS4 capability available as well. So we'll deal with that a little bit later. Let's just talk about iSCSI. So all you have to do basically is take that iSCSI software driver, excuse me, and bind it. There's a binding that is done, and in my previous course I showed you how that was done, and this is also bound. There's a binding that is done. So two bindings, right? So the iSCSI software driver knows that it has this path available for doing I/O and this path available for doing I/O, and what it does is it does multipathing I/O. Key consideration is only one active, only one physical NIC active at a time, and I believe you can have up to 4 iSCSI VM kernels. Okay, so again, make it nice and clean, put it in a different port group, just so that it's just easier to handle that way from an operational perspective. If you're using DVS, you just have to do it once. It's available everywhere else, and your design and your implementation is very simple and easy to operate. Okay, so I believe, and check the VMware documentations. Last I recall, I think the limit was 4 iSCSI VM kernel ports. So coming out of the ESXi host, you can have 4 different paths going out, and of course, then if you have multiple storage ports and storage processors on your iSCSI, and it allows you or it doesn't allow you LACP bundling and things of that nature, obviously you get even more paths across on the other side. So the number of paths that go through can multiply like crazy. But at least coming out of your ESXi host, I believe you can have up to 4 iSCSI VM kernels. So your traffic is spread throughout those available kernels. Let's switch gears now to NFS. Let's talk about NFS storage. And after NFS, we will deal with the TCP/IP stacks. So this is NFS storage. Normal, it was NFS 3 over TCP. Over UDP was not supported. Now you can have NFS 4.1, and that is supported. And that basically gives you multipathing also. So always a good thing to see if you can use NFS 4.1. The issue really is at this point is that not too many devices, storage arrays, support NFS 4.1, but there are many that do. So if you have one of those, you can actually try out NFS 4.1. So to go back to an NFS design, the way NFS is done. So let's look at the workflow for doing one of these things. Okay, so you have you are in the workflow for creating a data store. So the question that is asked, what kind do you need? VM FS, or you need virtual walls, or you need NFS. Okay, so you say I need NFS. Then it goes down and asks you server IPs, okay, plus mount point, right? It asks you this normally. It asks you what host you're on. In vSphere 6, you can specify multiple hosts, right? And basically, that's it. So the server IP really plays a very big role in NFS here, right? So the way that that is done with NFS. So let's look at some of those things that we need to consider for NFS. So we're back to NFS. Suppose you have I won't put in numbers here. Just say talk in terms of this is all conceptual, right? So IP subnet A, and which implies subnet addresses are different between A and IP subnet B. IP subnet B. Okay, and this is assigned to VM kernel port 2, and this is assigned to VM kernel port 3. So that's your ESXi host side. Okay, now on the array side, it might look like this. And again, there are so many considerations here for NFS arrays because they have different capabilities. Let's just see if we can stay conceptual here. Okay, so suppose it has 2 storage processors, usually storage processors. So let's just say there are 2 storage processors. Okay, so this is a storage processor 1 and storage processor 2, and you actually have them running. They usually have 2 NICs each, and they have usually the capability nowadays of doing LACP. Okay, now let's draw the network here in the middle. Okay, so this is your network. Okay. Now, a nice and simple, clean design would basically say that usually there's an alias address here, okay, on one of these ports. Okay, one of those ways you can do it is that you can LACP this thing, bundle this. You can bundle this. I'm not considering the physical network because you could run a VPC here really, which is a good thing to do because you can take one of these and it goes to switch A, and your Nexus switch A. This could go to Nexus switch B, which could be running a VPC. That's always a good idea. But the key here is that if you put this in IP subnet A and you put this in IP subnet B, with NFS 3, you would be basically having your traffic flow, your TCP session basically going like this. Now, of course, because you're good enough to spread it out across a VPC, you still have different ports for redundancy and resiliency, but really there's only one session here. Okay, so multipathing is really not possible, and the way it works is that we just remember the workflow. It'll pick up the first VM kernel port that's in the same IP subnet. So this VM kernel port will show up there because it's in the same subnet A as your NFS server here, right? And so this VM kernel port will be used for all traffic to IP subnet A. And if you have a completely separate subnet, then a different path will be obviously taken through because you can define your path, your physical NICs here that would be used for this port group. You can define the physical NICs that will be used for this port group, and you can spread your traffic out. A really good way to do it is to use load-based teaming as well. Okay, so use load-based teaming, and the different port groups will fend for themselves. Really, that's the way it actually works out in real practice. But the point of this is that with NFS, it's a very clean configuration. It's not like the iSCSI, where there is like a NFS driver, so to speak. Of course, there is NFS client, but it kind of works differently from the iSCSI software driver, where you are able to do multipathing. Okay, so basically single session. This is a nice clean way, in my opinion, to do this. Okay, you can have if you have the capability with your switches. Okay, put these in a link aggregation group 1. Put this in a link aggregation group 2. Don't do load-based teaming, of course. In that case, it's kind of pointless. You can do it this way, or of course you could use the load-based teaming option as well. It's really up to you. All right, so keep it simple. IP subnet A to IP subnet A, and use your knowledge of Cisco physical network design using VPCs and port channels to actually make this all work. Now, in this context, one interesting question that always comes up is, well, how do I know that if I have multiple links in a lag? So I'm going to draw a lag now. This is a lag. Okay, I have link 0 and I have link 1, basically 2 physical links in this link aggregation group. So the question comes up, well, how do I know which of these links is going to be used for my traffic? Now, in most cases, the algorithm that is used is based on source IP and destination IP. That's the most common way of doing it. Now, in ESXi 6, when you define when you use LACP, there are 23 load balancing options available. So you can do it on a 2-tuple, which is source IP, destination IP. You can do it on a 5-tuple as well. So source IP, destination IP, source IP, destination IP. You have protocol and source port and destination port. If you use this for your hash, it's a 5-tuple, 5 different things here to hash around. And if you do this, then obviously you have a much better chance of spreading traffic out in a more optimal manner, right? Now, interesting things apply here. One, knowledge base article. So at kb.vmware.com, there is an article. Do a search for it. KB article is 1001.371. This describes the algorithm that VMware uses to spread the traffic out across a static Ether channel. Okay, so this is not really for what we just talked about in terms of LACP. Okay, there may be some other information out there that tells you how this is done, but I think it's pretty straightforward, because you look at your 23 different options and you understand there's a hashing basically that happens, and then depending on your network and your and how you want to do this, you can do that. Among the 23 options here, I actually like VLAN quite a bit, because then it makes it very simple. If I just say give it based on VLAN, the port groups have different VLANs, and I know as long as I go VLAN 1, 3, 5, 7, and I have 2 physical links, okay, my traffic is going to stay on that same link. So the odd ones will stay on one link, and my even ones will stay on the other link. That's the way hashing would work. Unless it's really more complicated than that, I doubt it. I think this would probably do the trick, but of course requires you to use multiple VLANs, which makes your operation and design much more complicated. So while it's conceptually wonderful, I think really it is kind of difficult. So that look at this, and basically what in there they describe, they take the source IP in binary, and they exclusive OR that with the source with the destination IP in binary, and they apply a modulus to it, which is equal to the number of physical NICs. So if you have, say, 4 physical NICs, the numbers in the hash come out from 0 to 1, 2, 3, and that's how the traffic is actually distributed across that. Now I'll clear this, and we will take a quick look at some of the things you could do from a Cisco network side in trying to understand how the traffic would be distributed. And again, usually it's not that difficult. So let's see. First of all, you can say show port channel traffic. When you do that, you basically get all your port channels, and you get the receive unicast, transmit unicast, you get transmit unicast, you get receive unicast, right? Obviously you get receive mcast, multicasts, and transmit multicasts, right? And you receive broadcasts as well. So transmit and receive unicast, multicast, and broadcast on that channel. This is the channel group, port channel, right? Channel number. You get that. So show port channel traffic is a very useful command. Another command that you can use in Nexus is, this is an interesting one actually. It says show port channel RBH distribution. Show port channel RBH distribution. And what this shows you, it shows you channel ID. So if you have a port channel, say 10 up here, it shows you what your member ports are. So assume there are 2 of them, right? Ethernet say 1 3, and Ethernet say 1 4, and then there's a column which is the RBH value, right? So this is an RBH value, and this gives you the values basically of the hash. So in this case, for example, it could say 4, 5, 6, and 7. In this case, it's 0, 1, 2, 3. So, and then there's one which is called buckets. So obviously there are 4 buckets in both cases, right? So this kind of a hash is there, and you can get the value. So basically what it's saying is that if the hash value comes out to be 4, 5, 6, 7, then traffic will go to member port Ethernet 1.3. but how the heck are you going to actually do this in real life, right? So the next command is the one that you are actually looking for, which is a slightly long command, but it's a really neat command. On Nexus, show port channel, load balance, interface, port channel, and of course we all know we can short form this, say port channel 10, SRC, which is obviously your source IP, say is 172.20.10.3. That's one of my hosts, and I have my destination IP as say 172.20.90.1, which is one of my iSCSI arrays, and how many links I have based on a modulus. So you can say module. It actually I don't know why to say module, but that's the syntax. Say module 2, and what it does is it basically comes back with RBH equals, and there's a hex value for this. Say hex 2, right? And it says that actually translates to, which is really what we are looking for, is output. This is output port ID is your Ethernet 1/3. That's what you are looking for. So you give it the information. It's not that difficult to remember actually. Show port channel load balance for interface port channel that source IP destination IP with a modulus of 2, and it tells you what link it is going to go upon. So this is a really useful way of finding out on Nexus based on source IP and destination IP how the channel is going to actually assign the link to send the traffic to. The only other thing that's left for us to consider in terms of design concepts is to look at TCP/IP stacks. So with the Nexus, and I talked about it briefly before, not with Nexus, with vSphere 6, ESXi 6, what happens is when you install ESXi, you get 3 TCP stacks: default, provisioning, and vMotion stacks. In the beginning, only the default stack is used. When you actually assign VM kernel for provisioning, VMK kernel say 2, say VM kernel 4, when you actually assign these, when you create these VM kernels and you actually start using these other default TCP/IP stacks when during the workflow for creating these VM kernels, that's when these start actually getting used. Now obviously what we are looking at here is that the default TCP/IP stack has a gateway address, right, which implies the gateway to a physical network, for example. Now it's really interesting because you can, with provisioning, you can have a gateway also, right? It could be the same or a different, probably, because you probably have it on a different subnet, maybe not. Not going to get into it. So really going to have gateway 1, gateway 2. You would have a gateway 3. From a design perspective, that now gives you a lot more flexibility because you can now separate out your networks and your network devices. Now, with version 6 of ESXi, there is this most exciting possibility now of actually roll your own TCP/IP stack, right? And I think we are going to use it for IP storage. Okay, so you can use it for iSCSI or your NFS storage. Now, during my NFS discussion, I didn't really go into version 4. Frankly, it's very new, and some good design guides need to be made available to make sure that we all understand how best it is to use NFS version 4. But certainly, the documentation is updated very often by VMware. So if you're using NFS4 for example, then please just you keep on looking at NFS version 4 documentation on VMware, or look at the VMware blogs to see how one should best design an NFS 4 network, because that allows you multipathing I/O. Okay, but to get back to the topic of a TCP/IP stack, basically now you can have your gateway there as well. So you can have your gateway iSCSI, and that takes you off to your IP storage network, and that's always a good thing, because you don't want to mix up other kinds of traffic on your storage traffic. This, because remember, iSCSI is of course fiber channel SCSI traffic, SCSI protocol, which is also used with fiber channel over TCP. So using the same SCSI protocol internally, except it's encapsulated now in TCP frames. With fiber channel, it was encapsulated in FC frames. FC frames and the whole fiber channel network was designed to be lossless. So you do not want your TCP sessions to drop for any reason, or TCP to go into slow start mode and things of that nature. Best is to keep your IP storage traffic separate. Same thing applies for NFS. NFS version 3 is over TCP, so you have the same situation. You don't want to go into TCP, a slow start because of congestion, right? That's the last thing you need. So keep your IP storage completely separate, and make full use of the new capability, the roll your own TCP/IP stack. You get your own gateways, and as Cisco network engineers, you know what to do when you have gateways. Give them a nice new network, their own network to actually work on. This will save you a lot of operational grief. So we are now back at our slide here after that invigorating discussion around NIC theming and the details around design, the various options you have, the pros and cons. We did the same thing with load balancing and link aggregation groups, and we saw how we could actually use some Nexus commands as well as some algorithm and a little bit of math to figure out on the VMware side how the traffic, at least for a static ether channel, is going to be distributed across the links. We also looked at IP storage, NFS, iSCSI. We looked at some suggestions and recommendations. Keep it really simple. Give it its own network, its own storage network, so you can mimic fiber channel as much as was as you can, and that really would be a really good strategy. You really don't want issues on your storage network. It affects everything. Remember, in ESX, while we've been looking at and discussing it from a point of a single host, really for storage, clusters use shared storage. So there's a lot of traffic on your IP storage network. It's not just a one host situation, it's a multiple host in a cluster situation. And with the clusters now getting to really large sizes of like 64 hosts and so on, it's something to really watch out for. So last parting thought on this design concepts building blocks is mimic fiber channel storage as much as possible. Fiber channel storage kept two separate paths. There was your SAN A and a SAN B. Keep your sanity and design your IP storage network in exactly the same way. So with that, we are all primed to jump into our case study. I hope you're excited.